Okay, so we're talking about points of tangency today. So by definition, I want you guys to write this down, and I'm going to read it out loud while you write it into your notes. Today's date is, Xavier's not here, so today's date is the 25th. Okay, a tangent line in the same plane as a circle. A tangent is a line in the same place as a circle that intersects a circle in exactly one point. The point where the tangent and the circle intersect is called the point of tangency. So in this case, this P right here, this is the point of tangency right here. And I call it oftentimes, I usually call it the pot. Point of tangency. Okay? So there's the pot right there. All right. The pot is the point of tangency. All right? So we're moving on, and we're talking about circles, not so much like segments and sectors and arc length. We need all that. We're going to need that for our test. But now we're going to move on, and we're talking about points of tangency here, okay? Now, there is a connection between tangent lines and SOHCAHTOA tangent, okay? I don't know if I'm going to be the one to explain it or not, okay? But yes, those two words are related to each other, but right now we're going to separate those ideas out. We're going to pretend like we're just using the same word for two different ideas. But there is a connection in math, and maybe someday we can talk about that, okay? All right. So, as we just learned through our experiment, I'll let you finish this up. We learned a very important thing here with points of tangencies and radii. Okay? Very important concept we just learned. Now, it needs to be a provable fact. I'm not going to do the proof with us. Just know at this point in our career, we just know there's a proof out there. We wouldn't call it a theorem if we didn't have a proof, okay? It's what we did in our experiment today was not a proof. It was just a way to kind of get into a theory. All right, here, Cody, I'll take this one. All right, so Cody is using the construction tools as fidget spinners. All right, so now we're going to go ahead and we're going to get that theorem into our books, and we're going to use that whenever we want, and it's called the tangent radius theorem. Okay. If a line is tangent to a circle, then it is perpendicular to a radius drawn at the point of tangency. Okay? And Xavier, I am making this up and I'm recording this, so you can just pick up from here and then we'll go. All right. Thanks, Xavier. All right. So when we have this, ladies and gentlemen, we kind of saw that relationship there. We did a bunch of different tangency points, and every time we drew a radius to those tangent points, they all seem to be about 90 degrees. We agree with that with our project there, our little quick project. So that is a rule. Now, anytime in mathematics you get a right angle, it is a very important thing. Do you guys understand that? Right angles are very, very valuable in mathematics. They are huge. Anytime two lines are perpendicular, that is always a very helpful piece of knowledge. Okay, right angles are very important because right angles, perpendicular lines, we can use the Pythagorean theorem and trigonometry if we need to. Okay, we can form triangles and we can use Pythagorean theorem and trigonometry. So when you get a right angle, you should be very excited about that, okay? Because you now can get a right triangle if necessary, okay? So that's huge. A right angle is always a huge thing in mathematics, okay? So don't underestimate perpendicular. It's a huge, huge, huge concept. All right. So the converse of that is also true. Okay? If a line is perpendicular to the radius of a circle at the point on the circle, then it is a tangent. It's a point of tangency. Okay, so you can say, if you're not sure if a line is a point of tangency, a point in a line is a point of tangency. If it's perpendicular, then you know it's a tangent, point of tangency. Okay, so it goes both ways. So the converse is true. So this is actually a biconditional statement. We haven't talked about that for a while, but this is a pretty solid theorem here going on because it's biconditional. It goes both ways. And what we're going to do next is we're just going to do some example problems where we can actually apply this concept, okay? We can apply this concept and use prior knowledge of geometry to solve some problems. So we're just adding this nice little concept into our geometry, kind of like our geometry workbook. Now we have a new method to use, right? We have lots of methods in geometry. That's what basically we've been doing all year, is just getting all this good information in geometry and theorems. And now we've got a new one. And let's see if we can apply it to some geometry stuff, okay? So I'll give you another second, and then we'll do some examples using this nice theorem we got today. All right. So here's the first example. Okay, I'm going to call this example 1. So I want you to go ahead and sketch this example down. This is example 1. I'll give you a second to sketch this down. All right, so I want you to draw this picture here. And what I've done is I've created a shape. I got a circle. I got a center point. And I'm telling you right now that B and C are points of tangency. Excuse me, B and A are points of tangency, and C is the center point. And we want to find the measure of angle C. Okay? Now, if this looks familiar, if you notice, guys, this is very valuable, very applicable in especially astronomy, because what we can do is we can figure out angles between planets, we can figure out degree, and we can start to find missing measurements of planets and things like this. So the planets, or when you're talking about radar, like a satellite, okay? Lots of good things. If this is a satellite D out in space, and this is just like a 2D image of the Earth, you could say, well, how many degrees is that satellite going to hit the Earth? And, if you're listening to, your favorite podcast that's from a satellite, you're only going to be able to hear it at this portion. So there's lots of good information here. All right, now, so the first thing we want to do is we want to use our information that we now know, our theorem. So can we add some more information to this picture just by knowing what we now know? What?
Angle DAC is a 90-degree angle.
Right. Angle DAC is a 90-degree angle. See that? What else do we know? Xavier? Yeah, and we know that because these are points of tangency, and CA and CB are radii. So what kind of angle are we really looking for? We're looking for this angle. What's the name of this angle right here? What do we call an angle formed between two radii? The what? The central angle. Remember, this is the central angle. So basically, this question is asking for you to find the central angle. Okay? So let me do this because I want to get that other. Okay, the central angle. So this is the central angle. So we probably want to put that into our notes also, because it sounds like we're trying to figure out what the central angle is, right? You guys see that? Okay. Now, here's the deal. How many degrees is that central angle going to be, and why? Why? How could we figure out that central angle right there? Sophia?
Since it's a quadrilateral,
Yep.
you could do 360 minus 90 minus 90 minus 30.
Very good. Yep. And so, what is that angle right there? 360. So it's a quadrilateral, 4 sides. Okay. It's actually, I think, a kite, by the way, right?
Yeah.
Yep. So we could use all our kite properties if we wanted to. I don't think we'll need them here.
147 degrees.
Okay, so Martin's saying 147 degrees. You guys agreed, Martin's saying? Like that? Okay. Now, here's what I want to know now is, so let's just see if we understand the last week's material. So I want to know, what is the measure of arc AB equal to? I want to know the measure of arc AB. Now remember, when we're talking in the minor arc, right? So now let's see if you remember. This is we can connect a little bit what we've done. Now we can actually figure out the measure of arc AB. Okay?
That's correct.
So who can raise their hand here and tell me, what do we know about central angles and their intercepted arc? So this is a good get you back into your notes a little bit with central angles and intercepted arcs. What do we know about those?
Okay, so formula.
Okay, so let me help you out. So if you have forgotten, the measure of the central angle, I'm just going to say at CA first, central angles. Is that right, guys? The measure of angle, what is it, Chris? You got an ooh, what is it? The measure of the angle, the central angle, is equal to what? The measure of its intercepted arc. Now, we're not talking about the arc length. We're talking about the measure of this arc. So if the central angle is 147, class, what is the arc AB equal to? 147. Okay. Those are the same. Did we talk about that, class? Did we talk about central angles are always equal to their intercepted arc? Now, remember, we measure on an arc. We always measure an arc in degrees. Now, if we want to take that arc and cut it out and lay it out in a straight line, then that would be the arc length, right, guys? So now what I'm going to do is I'm going to add one piece of information here. I'm going to say that this is 12 centimeters long, the radius. So now what I need you guys to do is find the arc length. Okay, now I want you to find the arc length. So I want to know, what is the arc length of CA? Okay, so arc length of CA. So now this is a good review of arc length that we've already done.
Just the formulas. What's the
Well, we're in degrees, so you want to use the degrees formula, right?
That's true. I don't think you were. I was not here when you guys did. Oh.
Can someone remember what the formula is? What is it, Xavier? So theta over 360, because we have degrees, times 2 pi r, right? So remember, we always want to leave our final answer in pi, and then round it if we need to, right? Okay, so in this case, we have 147 over 360. Caitlin, you have your calculator out there. Can you help me? What's 147 divided by 360?
0.4083.
Okay, so now multiply that number by 2.
0.816.
Now multiply that number by 12. What is it? 9.8. So Caitlin is saying that we have approximately 9.8 pi. You guys agree with that? Okay. So hopefully you do. So we get approximately, in this case, 9.8 pi when we put everything in. And then if we wanted to even approximate that more without pi. What is that, Caitlin? About 30.8 centimeters. You guys see that? Now, notice, class, we would not have been able to do that problem right there if we didn't know that those A and B are right angles. You guys understand that? So this problem would have been a dead end for us last week. If I would have given you this problem, you would not have been able to figure out the arc length because you wouldn't have had the central angle yet. Do you guys understand that? But now we can actually we can move on. So before then, when this would have been a dead end problem, now it's a problem we can solve, and that always feels good, right? Okay. Now here's a fun problem. Draw this out for me. This is a really good problem. Okay. I will put this problem on the test, by the way, just different numbers. Absolutely. I always put this problem on the test. Okay, so I want you to draw this out. It kind of looks like really what this problem is. This is a good, have you guys ever heard of something called a bicycle? Okay, a bicycle has two sprockets. Okay, the basic bicycle, if it's not it has the front chain ring, and then if it's just a one speed, that's the back, right?
Oh, mine's a 3-speed.
And what happens is the chain goes around.
Mine's an 8 in the back.
Okay?
Oh, yeah.
The chain goes around the big one and the small one, and it propels you forward, right? With some other mechanical stuff. So you can think of a chain sometimes, not exactly, but a chain is kind of like a tangent. Not exactly. Now, if I want to figure, so what I'm trying to figure out in this problem is, I want to know the distance between A and D. Okay? So I really like this problem. So copy this out. We have 10 minutes to finish it. I think we can do that. I really like the problem. I really like this problem a lot. Okay? So you might want to say this is a test problem. So I would definitely, I'm gonna promise you, I will put this kind of problem on a test. It's just kind of a classic geometry problem. Okay, it's one of those problems like in geometry and math, like leaning a ladder up against the wall is really, as you move on through math, leaning ladders against walls are really they always come up. Or people standing out and measuring flagpoles outside with shadows. Those are classic math problems. Okay.
No, I love when the average person just needs to use their shadow to find a
Well,
flag.
yeah, of course. Okay, now,
So reasonable.
so here's what we're going to do here. Our job is to figure out this distance between A and D. Thank you, Sophia, because, yeah, I think you are right. The average person does need to know those important skills. All right.
I'm not an expert, Mr. Roden, and I think she might have been joking.
Okay.
Oh,
No.
yeah.
All right. Now, so we need to figure out the length of that green line right there. So here's my question. Just by looking at this thing, looking at this picture that we have, looks like we have a quadrilateral, right?
That's true.
Is there anything we could do here right now to figure out the the length of the green line? Any ideas?
I forgot.
A trapezoid would require parallel lines, right? And I don't know, we don't have a pair of parallel lines here as far as I know.
They
Okay.
don't look parallel to me.
I mean, they could be parallel, okay? So I don't think we can do that. But parallel lines would be really, really nice, right, guys? So let's do this. Okay, let's actually do that. I like what you're thinking there, Xavier. So what we're going to do is we're actually going to we can always construct a parallel line through a point. If we have a point and another line, we can always construct a parallel line, right? So I'm going to start at A here, and I'm going to construct a parallel line, the line that's parallel with line BC. So it's going to look something, it's got to be parallel. So it's going to look something like this. Okay, guys, got that? So that looks pretty parallel. I'm going to make that line blue, by the way. Okay. So I just constructed a parallel line between A and the radius of the big circle. You guys understand that? And remember, when you have a point and a line, you can always construct a parallel line from it, okay? Okay, now, what other piece of information, class, do we know from our learning today? Okay, there are tangency points. Why is that nice?
It's a right angle.
What are right angles?
90 degrees.
Tell me where the right angles exist.
A, B, C, and D.
Okay, they exist. Well, we don't know about A, but we know for sure that we have a right angle right here, and we know we have a right angle right here. Okay, could we say that this is a right angle right here? Because of what? This is a rectangle, right? See that right angle right there? So I guess so now we have a rectangle. Now, here's my question though. Have we found can we figure out the green line though? No, we can't. Well, we know there's a right angle right here though still, right? So, we have a right triangle in here somewhere. Remember the power of right triangles? You guys see where our right triangle is? Right here. I'm going to highlight our right triangle. Let me highlight it here. I'm going to highlight it in purple. Ladies and gentlemen, we have a right triangle right here. You guys see that right triangle? Sorry, it's kind of messy. Sorry. I'm going to get rid of that in a minute. See that right triangle right there? Okay, so you know what I'm talking about. That's a right triangle. Now, we actually know some measurements here. Do we know the measurement of the blue side of this right triangle? Yes, we do. What is the measurement of the blue side, class?
26.5.
Because it's the opposite side of the rectangle. It's a parallelogram. Opposite sides are parallel. Okay, now, we don't know the green line, but let's see here. Can we figure out what this measurement right here is? It's not 9.3. 9.3 is the whole thing.
It's 9.3 minus 2.5.
It's 9.3 minus this amount right here, this 2.4, because this is 2.4 right here. So that measurement is the 9.3 minus 2.4. Very good, class. And what is that measure right there, class?
6.9.
So this now, let me get rid of this. 9.3 is the whole thing, but that little piece right there is 6.9. You guys see that? See that 6.9 right there? This is 6.9, and the whole thing was 9.3. Now, we can use the Pythagorean theorem to figure out the green line. So now we have a squared plus b squared equals c squared. What is going to be our c in this case, class?
Green line. AD.
8. What? No. Where C is always, our C is the green line, right? AD. It's opposite the right angle. It kind of looks like the blue line is, but it's not. It's the green line is our, so we don't know what C squared is, but then we can say, what is A in this case, class? What can we say A is? 6.9 squared plus, what can we say that B is, class? 26.5 squared equals C squared. Now we use our calculators. Since Sam has his calculator ready to go, I'll just pick on him. Sam, what is 6.9 squared?
6.9 squared is equal to 47.62.
Okay. Sam, what is 26.5 squared?
26.5 squared is 702.25.
Okay, 702. That's 702.25.
Yep.
Sam, add those up. What's 47.62 plus 702.25?
749 and 8600.
749.86. And then what do we have to do, guys? Because that's c squared. What do we have to do? Square root. Sam, can you take the square root of that, please? Now we know that.
27.38.
And that's very reasonable, right? Because we know the green line has to be longer than the blue line because it lies opposite the right angle.
Right.
You guys see that?
Yep.
So think about all the knowledge we just used on this problem right here. We really used our knowledge of rectangles and parallelograms. We used our knowledge that we can always construct a parallel line. We used our new knowledge of tangency and right perpendicular, right angles. We used, what else did we use? We used the Pythagorean theorem. We used,
Subtraction.
just basics. There's so much stuff we've learned in here, and just this problem is packed with information. Our opposite angles theorem to check that, hey, this green line, if this came out less than the blue line, then we know we did something wrong, right? So just a lot of really good information in this problem right here. Okay, so we'll move on tomorrow using this. We're going to talk more about points of tangencies on circles tomorrow. There will be homework tomorrow, but not today. Okay, so I'll announce the homework tomorrow. I'm not ready to give you homework today.